When we were in class, I actually gave you a bit of an outline on how to solve problems, but I'd kind of like to review that right now. So, how to approach force problems. And this is what I'd like to say. First, don't read the problem yet. That's the first thing. The second thing, use the picture to draw a free body diagram. Next, see if there is friction. And finally, once you've got that free body diagram, okay, read the problem, then set up balanced to unbalanced forces in X and Y, that's Newton's second law, and solve everything, even if the problem doesn't ask for it. Okay? That's the approach we're going to use on problem number 3. So let's actually set up our free body diagram. Do not assume these two chords have the same tension, and I'll show you why in a second. So let's just kind of divide this down the middle. We have an isosceles triangle, and I know the two thetas here will be the same because it is isosceles. So I'll call this angle theta, and I'll call this angle theta. And we're going to set up our free body diagram right here. Make it a little bigger. So I'm going to have the weight of the ball due to the earth. I'm going to have T1 here and T2 here. These lines are atrocious. That looks just awful. I think I'm trying to draw a Voldemort serpent Nagini, and I'm doing a terrible job. Those are supposed to be perfectly straight lines. So this is theta, and this is theta. And now I'm going to use SOHCAHTOA to break down these forces. So this here is going to be T1 sine of theta. And then horizontally here, I'm going to have T1 cosine of theta. For T2, I'm going to do a similar breakdown. I'll have horizontally T2 cosine of theta, and then vertically, I'm going to have T2 sine of theta. All right, let's just check. Do I see the word friction anywhere in here? No, I do not. Oh, another thing. You notice how we're not resting on any kind of a table? So that means that there's no normal force in this problem. And in fact, just a small little hint. This is not for everybody, but no surface implies no normal force. Okay, so that's why there aren't any normal forces in this problem. Now we can go ahead and actually read the question. So we've got this 1.34 kilogram ball. Each rod is 1.7, so these are the same length. Sorry, each rope. And then the separation distance is also 1.7. So check this out. This distance here, when I read the question, it says d is 1.7 meters. That tells me this here is L over 2, and this is L over 2. And so I actually conclude that this is a 30, 60, 90 triangle. Okay, so I wrote this in orange. Okay, this fact, okay, this D equals 1.7 meters. This tells me it's a 30, 60, 90 triangle. That's how I'm able to tell that. So now what I can do is I can go ahead. They want to know the tension in the lower string, the net force on the ball, and the speed of the ball, and the direction of F net. So let's go ahead and set up Newton's laws in the x direction and in the y direction for the ball. So first of all, this little thing, it does not move up. So we'll just note something here. In the y direction, we'll just say this, I'll say it like this. It does not move up or down. It only moves in a circle. That's all it does. So what this tells us, this little fact here means that in the y direction, we balance. And in the x direction, we accelerate. Horizontally, we accelerate because we're moving in a circle. Now, these aren't fraction signs. This is just me making little columns here in order to solve the problem. So vertically, I'm going to actually read the forces as they're written here. So I have this arrow and this arrow and this arrow. Arrows 1, 2, and 3. Three. So in the y direction, I have those 3 arrows. And I'm going to actually write down the force equation as T1 sine theta minus T2 sine theta minus WBE. And all those forces combine and they actually cancel. They balance because we don't see any vertical movement in the ball. Now in the x direction, we're going to have T1 cosine theta and T2 cosine theta. And the effect in their direction is that the ball accelerates in a circle. But this is circular acceleration, so I'm actually going to go one line further here and write this as T1 cos theta plus T2 cos theta equals mv squared divided by r. Okay, and let's be clear here. The radius here, I'm just going to draw it in a different color. I'm just going to be clear here. This thing here is the radius. That's the radius. And to be clear, the radius is going to be L square root of 3 over 2 from SOHCAHTOA and 30, 60, 90. Okay, that's how I'm reaching that conclusion. So, to be clear, let's go ahead and we can set some things up. So our goal is we want the tension in the lower string. We're going to go ahead and get the tension in the upper string too, just to be clear. So we've got T1 times the sine of 30 minus T2 times the sine of 30 minus, now the weight here, let's be careful, that's M times G. That's going to be 1.34 times 10. So let's be clear, we're going to end up getting here T1 over 2, because sine of 30 is a half, minus T2 over 2 equals 13.4. And we can just say T1 minus T2 is 26.8. We really can't do any more with that, so we're going to need to go to the second formula. So in the x direction, we're going to say T1 times radical 3 over 2 plus T2 times radical 3 over 2, because I'm putting 60 degrees in for the this is the cosine of 30. Okay, and that's going to equal 1.34 times v squared over, now I'm going to do a little work with fractions, that's radical 3 over 2, but the 2 goes on top, times this L, which is 1.7. Okay, so this R is radical 3 over 2 times L, and L is 1.7. That's how I'm reaching these conclusions. Okay, so in fact, let me just be clear on this. This is radical 3 over 2 times L. And just so you know, this is the radical 3 times 1.7. And then the 2 goes on top because that's how fractions work. Okay, so there's a little bit to simplify here. Let me just go ahead and do that. And here we go. So I've got here, so this is just going to be, I hate that color when it's not being used to denote anything. 0.87 T1 plus 0.87 T2 equals all right. Now we have 2.68 divided by the square root of 3 divided by 1.7. I'm getting this as 0.91 v squared. I'm just going to double check those numbers one more time. All right, oops, one more time. So 1.34 times 2 divided by the square root of 3 divided by 1.7. Yeah, 0.91 v squared. So is there any other, it looks like we've got 3 variables. Let's reread the problem and see what's missing. So the tension in the upper string is 35 newtons. Yay. So I have 35 newtons minus T2 is 26.8. So I reached the conclusion that T2 is about 8.2 newtons. And I can actually go ahead and use that right here. So I get 0.87 times 35 plus 0.87 times 8.2 equals 0.91 v squared. Very nice. So I can actually go ahead and do a little bit of math here. And when I get this speed, I end up getting a speed of 6.43 meters per second. So have I solved for everything? Let's see. We got the tension, we got the speed. Now the magnitude of the net force F net. Well, F net is going to be m times a, which is going to be 1.34 times 6.43 squared divided by, well, the radius is going to be 1.7 times square root of 3 over 2. That's 1.47. And let me just actually kind of write out the math here as to how I got that. Let's remember, the radius is radical 3 over 2 times L, which is radical 3 over 2 times 1.7. So when we actually end up getting this F net, that's 1.34 times 6.43 squared, whoops, divided by 1.47. And that's giving me a net force of about 37.6 newtons. And let's be clear, centripetal acceleration always pulls things to the left, and or to the center of the circle. And if we actually look, the net force points left. So let's just kind of label each part here. Going back and labeling our answers, okay, this is the answer to part A. This is the answer to part B. This is the answer to part C. And this is the answer to part D. So that is problem number 3.